Example2Mul.c is the hexadecimal Hannibal Lecter of examples because dissected delectable. But in this example, we're going to use integer 128, so that's going to be something a little bit new. In integer 128, GCC has support for this. You do underscore underscore int 128a, initialize it to some hex value. Then we're going to multiply integer 128 times another hexadecimal value, and because of the way that C multiplication works, it's going to upcast this to be a 128-bit value, so it's going to do 128 times 128-bit multiplication. When we compile this at optimization level 0, we get the following code, which is actually pretty complicated given the fact that we just have two constants being multiplied by each other. So I was searching for something that would give me some multiply that keeps the high order bits. But little did I know when I stumbled on this example that I would be making things more complicated for myself by having to explain to you what's going on with 128-bit multiplication when you have only 64 times 64-bit multiplication instructions. Let's cover the instruction and come back to the intuition behind what's going on later. So first thing, multiply high unsigned. Multiply, keep the high xlang bits, and treat it as if it's unsigned times unsigned multiplication. Earlier, I had showed you the picture for 4-bit multiplication where we said the bottom 4 bits will always be the same regardless of the signs, whereas the upper bits will be different based on unsigned versus signed multiplication. So RISC-V consequently does different assembly instructions for whether you're operating on unsigned times unsigned, signed times signed, or unsigned times signed. This one is the unsigned times unsigned. So you've got your source operand 1 times your source operand 2. Assume that they're unsigned and keep only the high xlang bits, not the low like just a plain mul, but the high xlang bits. So that's exactly what that's saying. Again, just xlang sized RS1. So this could be 32-bit, could be 64-bit. Depends on how your code is compiled and what execution mode you're operating in. So xlang times xlang store the high xlang into the destination, which is xlang width. So I said that the multiply high unsigned is meant to be used when multiplying unsigned times unsigned. And we know that we're actually doing a signed integer 128a times itself, so signed times signed. So why are we seeing this here? Well, we'll come back to that after we cover a little bit more of the intuition, after you see the actual assembly code, step through every single line, make notes for yourself on every single line, and then you'll be clear on why this is happening. So just to put an example out there, we have mul high unsigned, T0 set to hex 20, which is 32, times T1, which we're going to set to 1 and all zeros. So that's going to be 1 and 15 zeros. So the result of this, because you have hex 20, and so you got 15 zeros and 20, which has 1 0, you're going to need at least 16 zeros and then a 2, but that means that that result can't possibly fit in a 64-bit value. So the net result of this is because we're doing the multiplication and keeping only the high, the upper 64 bits is just going to be the 2. And then if we do a mul to get the lower bits and store it into a different register so we don't clobber our T2, store it into T3, we get hex 20 times 1 and 15 zeros, and the net result is all zeros, these 16 zeros from the bottom 0 and the 15 zeros here. So the overall 128-bit value of this 64 times 64-bit multiplication is 2 and 16 zeros. Upper bits stored in T2 by the mul high unsigned, lower bits stored in T3 by the just plain mul. So returning to the code, I said that this was just me trying to create something small that would, store something into a 128-bit value so that we would keep the upper 64 bits. That's all I was really trying to go for. But, after playing around with various permutations and stuff, this was the simple form, simple in the sense of simple C, but this was clearly not simple assembly. We have multiple multiplications. We have mul, 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 and then mul hu. So I need to give you some intuition of how the compiler is going to generate a 128-bit times 128-bit multiplication. I had really just wanted to hand wave around all this and say, whatever. When you have, debugger support, you just walk through with the debugger, look at the values, and it'll make sense. But this may not have necessarily made sense, so I did feel I had to give you a little more intuition before I turned you loose in the debugger to see what's going on here. So the first point is that the compiler is doing A times A, which is 128-bit times 128-bit. The result should be a 256-bit value, but we're storing the result back into A, the 128-bit value. That means we don't need to even care about the upper 128 bits. The compiler doesn't need to generate code to create those values for the upper 128 bits. They'll just be thrown away anyways. So the compiler should only create code that generates the lower 128-bit values that will ultimately be stored and returned. So now I'm again borrowing some inspiration from this ARM Assembly for Embedded Applications book. And if you go look at his Chapter 5 integer arithmetic section, he talks about 64-bit times 64-bit multiplication in the context of ARM that was only 32-bit ARM. And so I'm taking the same principle of we're trying to do multiplication of variables that are too big for us to even hold in a register and for which we have no native multiplication assembly instruction. But the same principle that applies to 64 times 64 in the context of 32-bit code can apply to 128 times 128 in the context of 64-bit code. So first of all, let's say that we have a variable A and a variable B, which are 128 bits. So a different mathematical way that we could represent A, the 128-bit value, is as if it was two 64-bit values. The first 64-bit value, A high for the upper half, is multiplied by 2 to the 64. And if we think about that in hexadecimal, 2 to the 64 would be like a 1 followed by 16 zeros in hexadecimal. So taking any value, let's call it dead beef cafe babe, multiplying it by 1 and 16 zeros in hexadecimal is kind of just the same thing as shifting it up by 64 bits. So whatever your A high value was in hexadecimal, if you multiply it by 2 to the 64, that'll shift it up. It'll be represented up here. And then plus the A low value, whatever that was, will give you the overall 128-bit value that is A. So we're going to write it this way. And we're going to write B the same way of a B high and a B low. B high times 2 to the 64 and B low just added into the resulting value. And so if we want to do A times B, we're instead going to multiply these alternative representations of A and B. So A right here times B right here, where we've just substituted in these values up here. Now at this point, you want to do the multiplicative distributive law, and you would multiply these things out to get a result. Now I'm just going to say my ordering is going to come from the little mnemonic that they teach in algebra in the United States called FOIL. And so in FOIL, you do the first things multiplied together plus the outer things first. So first, outer, inner, and then last. FOIL is first, outer, inner, last. So the net result of doing that is going to be first, A high times 2 to the 64 times the first thing, B high times 2 to the 64. It gives you A high times B high times 2 to the 128, because the 2 to the 64 and 2 to the 64, the 64s can just be added. So that's the first. The outer is A high times 2 to the 64 times B low. So A high times B low times 2 to the 64. The inner, A low times B high times 2 to the 64. A low times B high times 2 to the 64. And then last, A low times B low. So it's the exact same thing as if you apply the proper generic distributive law. It's just a mnemonic that they teach. And that's the first thing that I thought when I saw this, x plus y times z times w or whatever. So this is going to be the result here. Now, we get the multiplication of A high times B high. That is a value that we can calculate with our 64-bit multiplication. So A high, upper 64 bits, times B high, upper 64 bits. We have a 64 times 64 multiplication, which we can get that. And then the times 2 to the 128 would kind of just be like as if it was shifted by 128 bits this way. So that's our first result. And then plus the next result, which is A high times B low times 2 to the 64. Again, A high times B low, that is a 64 times 64-bit multiplication. We have an assembly instruction for that. We can calculate the product of that, and the fact that it's times 2 to the 64 is just like as if it was shifted up times 2 to the 64. Then the next product, A low times B high, is going to be added in. So add in a low times b high times 2 to the 64. Same thing, we can calculate that. We can get the lower 64 from the mul instruction, the upper 64 from the MulHu instruction, and so we can get the full 128-bit value there. And then finally, the a low times b low, we're going to add that in, and that would be not shifted by anything. It's just a low times b low. But the key insight of these 4 multiplications plus additions is that that would be a 256-bit result. But we said we don't need a 256-bit result. We need a 128-bit result. So really, all of this stuff up here, we don't need to compute that. What we need to compute is this bottom 64 bits of that result plus the bottom 64 bits of that result plus the upper 64 bits of that result, and that'll give us the upper 64 bits. So just this plus this plus this, store it somewhere, that'll be the upper 64 bits. And then just this multiplication and just keeping the bottom 64 bits will give us the bottom 64 bits of the overall 128-bit result. So just to be more concrete about that, in the context of our a times, the other new constant, the dissected would be the lower 64 bits to start with, and then the 64-bit value that is upcast, it is just delectable, but it's upcast to a 128-bit value before it's multiplied times dissected. And so we really only need to do this a high times b low. So a high, which is zeros, times b low, which is delectable. Keep only the lower bits, and quite frankly, because you can see it's 0, the bits are going to be 0. And then the a low times b high. So a low times b high, well, again, 0 times anything is 0. So that's going to be 0. And so then ultimately this a low times b low, that is going to be a combination of a normal multiply to get the lower bits and a multiply high to get the high bits. And so adding this to this to this, that's what we ultimately are seeing in this assembly. So there's only one more thing that I need to show you before I let you loose on that assembly, and that is a reminder about integer calling conventions. And specifically, it said that there are 8 argument registers, A0 through A7, the first 2 of which are used in return values. So I'm telling you concretely that when we're returning a 128-bit value, A0 is going to be the least significant bits, and A1 is going to be the most significant bits. So with that, now you have the information necessary in order to go and read this assembly. And for this example, I highly recommend you literally copy and paste the assembly, put it into a text editor, and make a comment on every single line so that you know what's going on, and keep track of for each line, do you think this is a high, A low, B high, B low? Treat the dissected as the dissected is the A high to start with, delectable is the B, sorry, not A high. Dissected is the A to start with, delectable is the B to start with, and just keep track of A highs times A lows and so forth. You will see that again it's upcast to 128 bits and the upper 128 bits is 0. So that should give you, a hint that there's going to be some pointless 0 multiplication going on, but still walk through every single assembly instruction, write a comment for every line, and you should see that our intuition behind this sort of operation going on in the code that the compiler generated is what's actually going on. All right, go off and use your debugger, use some comments on the source lines.